Okay, back on track. Here we go. All right, we're talking about sample mean. So the mean of x bar is going to be the given mu, and the standard deviation of x bar is sigma over the square root of n. 10% condition still has to be met. Okay. Here are the criteria that will allow you to use normal calculations. This is different than proportions. So in proportions, we do the n times p and the n times 1 minus p, right? There's no p here, so we can't do that. So here are the conditions. Sometimes the original population distribution is normal. They will tell you that in the problem. So if they say that, then you're good to go. So that's case 1. The original population distribution is normal. So they tell you in the problem, hey, the population is normal, you're good to go. That doesn't always happen. So we have a second bullet that we're going to add here. Party Sabetti talked about this in her video the other day, and if n is greater than or equal to 30, so if your sample size is greater than or equal to 30, we can apply what's called the central limit theorem. The number 30 is a little bit arbitrary. Some books use 20. We're going to go with 30. Because as your population gets larger, as we saw in the video that we watched recently, as the sample size gets larger, the distribution is going to get closer and closer to normal. So we set this 30 as like the magic number. Okay. So if your sample size is at least 30, you can be like, hey, you're literally going to say the sample size is greater than 30, so I can apply the central limit theorem and use the normal approximation. Good. Let's do a problem. Suppose women's heights are normal with the mean of 64.5, standard deviation 2.5, and we select 10 women. We want the mean and standard deviation. Here goes. The mean of x bar is equal to the mean that's given, which is 64.5 inches. The standard deviation of x bar is the given standard deviation of 2.5 divided by the square root of the sample size. So this is about 0.79 inches. And again, we have to like add that because let's see, there are more than 10 times 10 or 100 women, I guess. Kind of vague. Just women, I don't know. There's more than 100 of us. Good. Okay, what's the probability that the mean is greater than 65 inches? Well, before we can do that, we have to check and see if one of our two criteria are met to use the normal calculations. So we don't know about the original population. It probably is normal because things like heights generally are normal, but we definitely have a sample size. Well, I guess we don't have a sample size. We're going to go with the original distribution is probably normal because it is a measurement of heights. Things like heights, weights, lengths are generally normally distributed. So I'm going to say that. Here goes. We will assume, we're going to do a lot of assuming as we move forward too. We will assume.
Oh yeah, it tells them us.
Oh, it did?
Yeah.
Did it tell me? Oh, look that. Sweet. Oh. We know the population distribution is normal. So we can use the normal approximation. Excellent. All right, I'm going to calculator. There I go. Normal CDF. trying to find the probability that X bar is going to be greater than 65 inches, 65 inches. That's what we're trying to find. So I'm going to go to my normal CDF. 65 will be my lower bound. Something big will be my upper bound. The mean is 64.5, and the standard deviation was 0.79. Paste. So I'm looking at about 0.26. So remember, I'm going to write down my, I'm going to make sure to write down these prompts that I put in. So on TI-84, normal CDF. Lower is 65. Upper, something big. Mean, standard deviation. And my probability came out to about 0.26. There it is. So now that we've gotten in a rhythm with the proportion one, the mean comes a little bit easier, right? It's just there's a different formula for the standard deviation and a different way to justify whether you can use the normal approximation or not. So the next question is, what is the probability that a single randomly selected woman has a height greater than 65 inches? That's a different question, right? So I just sort of backtracking. We've answered questions like this many times before, but it's important to understand that that is not a sampling distribution anymore, right? That is a single randomly selected person. So when you perform this calculation, which you're going to do right now, you're going to use the original mean and standard deviation, not the new standard deviation that we calculated for the sampling distribution. So right now, I would like you to find the probability that a single, not X bar, a single person is greater than 65 inches tall.
Is that like binomial CDF?
Nope, still normal. It's normal distribution, right? Population was normally distributed. Okay, so we're going with the normal CDF, and we still want 65 and something big, and we still have a mean of 64.5, but we're going to change this guy to 2.5.
What did you do?
So we're looking at about 0.42 for my probability. Yes? Good. Excellent.
That's embarrassing.
Okay, flip the paper over. And you are going to try number 2. So they're telling me that the distribution is strongly right skewed with a mean of 1 and a standard deviation of 1. I take an SRS of 70, and I plan 1.1 hours per call. And I want to know, is this going to be enough time? All right, so you're going to start by finding your mean and your standard deviation and making sure that you have met the criteria for the standard deviation. And then you're going to check to see if it's appropriate to use a normal approximation. Do that now. So we're front loading, right? We're like, calculating mean and standard deviation, justifying that the standard deviation is acceptable to use, and asking ourselves, can we use the normal approximation? Ultimately, the question we're looking to answer is, what is the probability that my call will take longer than 1.1